Very much. And yeah, once again, thank you very much for always being on time today. It's really amazing. So without further ado, I think everyone knows the rules by now. I'll pass it over to Fernando and Shamit that will tell us how to construct the sitter.
All right, thank you very much, Pedro. I hope you guys can hear me. If not, somebody send me a message. So I'd like to thank the organizers for giving us the opportunity to address the subject. And I hope next time we can actually be in Brazil. I've been there before. I'd love to go again. So with no further ado, I'm going to share my screen and then go through, a few minutes of slides. Then Fernando will do the same. I think we're going to be complementary. And after that, it'll be thrown open to discussion. So we were charged with discussing sort of de Sitter constructions in string theory, and I took the liberty of slightly broadening the title. And why would you talk about de Sitter space in string theory? Well, since 1998, if not before that, you need very little excuse. The subject is well motivated and has just been increasingly well motivated by data. The plot I have there symbolically is the latest DES data release. An Occam's razor interpretation of the concordance cosmology is that we live in a universe with positive cosmological constant. Other interpretations are possible, so that's of course not certain, but it seems like the right place to start. So in the context of string theory, if you're faced with this, the subject sort of splits into two interesting pieces, and the two interesting pieces could enjoy interplay. Okay, so one of them is, how do we arrange the ingredients in the theory to make lower dimensional de Sitter space? We don't live in 10 dimensions. We'd like to make, for instance, 4-dimensional de Sitter space. So I'll always parochially restrict my formulas to that. But how do we do that? Can we do that? And that really, in a glorified sense, it just involves engineering in extra dimensions. There are rules. We know a lot of the rules. It's a question of engineering. Then there's a second set of questions. Here there's more of a space-time diagram of de Sitter space. And the causal structure of de Sitter in the era after holography tells us that there are going to be interesting questions about formulating quantum gravity in de Sitter space. The asymptotics it provides are very different from those of Minkowski or anti-de Sitter space. There is no precise analog of a flat space S matrix or of CFT correlators that we've come to rely on as a crutch to make precise formulations. And this leads to a host of interesting questions, which I'll barely touch on. Okay, but hopefully the two subjects enjoy interrelations. So I'm going to focus on that first question. And really importantly, I'm just going to describe how I think about it. I understand different people think in different ways. I'm best qualified to describe my own thinking. I find it pretty simple, so let me lay it out. What is the basic point? We have a question about constructing de Sitter space in string theory. What that means, following the fine tradition of string compactification, we want to find 4-dimensional effective theories that arise after dimensional reduction with potential functions V that have minima at positive V. Okay, it's not rocket science. Now, that's not an empty exercise because the theory has constrained ingredients with known energetics. So it may or may not be possible. You have only certain building blocks. And so the first thing we should do is just try to get intuition. Is this possible or not? Which many of us started doing in the late 90s. Okay, so let's discuss some of the ingredients that are known to be in the theory. For instance, for critical strings on a compact manifold of basic size R, one of the ingredients that are present in, for instance, the type 2 theories are Ramond and NS fluxes. How do fluxes contribute to a potential? Well, there are more complicated formulas, but the simplest thing to do is you look at the terms in the Lagrangian containing the fluxes. There are some G's to contract them, and it's quadratic in flux. And if you take into account all the G's and go to Einstein frame in 4 dimensions, you get a potential that scales like a power of 1 over R. R to the 6th plus 2p for a p-form field strength. I'm going to focus on scalings with R. You could also focus on scalings with the dilaton just to get some intuition, because R, the size, and the dilaton are universal minor. So that's one contribution. Now, string theory also comes with D-branes and O-planes, D-branes and orientable planes. And if you have such an object wrapping Q internal dimensions and filling the non-compact space, you get a contribution of the potential that goes like the tension. It can be positive or negative, depending on whether it's a D-brane or O-plane, and the scaling is like 1 over R to the 12 minus Q. Importantly, for instance, if you take a 9-brane filling space in critical string theory, that doesn't just give you a vacuum energy from the tension. The rescaling to Einstein frame in 4 dimensions makes the scaling of that fall like a power of 1 over R, and that's why it's an interesting question to try and get, positive energy vacuum. Okay. Now, there are other potentially important sources of potentials beyond fluxes and D-branes and O-planes. A common thing that you first learn when you first open a string theory textbook, and then you conveniently forget if you focus too much on critical strings, is the leading term in the beta function, which goes like d minus d critical. That could be present. It could be important. We often focus, and I personally have focused a little bit parochially on Ricci flat manifolds on Calabi-Yau's, but if there's curvature, for instance, at the KK scale, if you're reducing on a curved manifold, that contributes to the lower dimensional potential. This is familiar to all of you from Freund-Rubin solutions that famously give, for instance, ADS5 times S5. The sphere curvature, importantly, contributes negatively. In theories that have supersymmetry beneath the KK scale, which are going to be my subject henceforth, it's usual to package the potential in a superpotential. One of the terms that's common basically captures this flux energy that I mentioned before, but also it's well known, it has been studied for decades, that there could be non-perturbative contributions to the superpotential. In a supersymmetric theory, for every axion, there's a corresponding kind of instanton. In string theory, those come potentially from worldsheet instantons or d-brane instantons, and they contribute in a way that's exponential in the volume, whatever cycle they wrap in the internal space. Okay, so you can quickly convince yourself that if you randomly were to mix and match the ingredients you have qualitatively and compute the structure of the resulting potentials, okay, it's easiest to get runaways or anti-de Sitter vacua, but in fact, vacua with positive V at minima do occur in toy models without really too much effort, okay? Now, it's important to say that global models that you can really write down don't allow random mixing and matching of these types of ingredients. They're constrained by tadpoles and by the fact that, for instance, the relevant features have to exist in the given manifold you're studying. So the fact that random mixing and matching makes it seem easy isn't at all decisive. There's more work to do. And in fact, the next level of thought, slightly more thought, will reveal a variety of limited, and I'll come back to this, classical no-go theorems. Two famous ones dating from the 80s and about 2000 are those of DeWitt, Smith, Haridas, and Maldacena Nunez, which basically show that in classical supergravity with a variety of ingredients, it's impossible to find stable de Sitter vacuum. Another set of arguments that, for instance, we generated with Taylor and others around 2007 show that even if you include some of the stringy ingredients, not all of them, but you include O-planes and D-branes of certain sorts that occur in certain models and certain fluxes, scaling arguments show that you can get positive energy, but you can't get a classical de Sitter vacuum. Okay, so the list of ingredients there was limited. It's sort of obvious how you go beyond the list of ingredients based on the assumptions of the theorem. Okay, and so now let me come back to this word limited. The limits are obvious. And indeed, those of us who started thinking about the subject in 2000 already built those in. And to my mind, we overcame those limits already, with the ideas of the early 2000s, though detailed implementation remains a challenging question. Okay, there are classical constructions that involve additional contributions from geometry and branes. They were discussed in TASI lectures. Gonzalo Taroba talked about a construction combining some of these ingredients together with a one-loop effect. And of course, physics isn't classical, and it's hard to stress that enough. That last point isn't only a subtlety that matters for complicated microscopic physics, it matters for macroscopic objects in our universe. On the scale of strings, atoms are macroscopic. It certainly matters for those. It matters for white dwarfs and neutron stars, some of the biggest objects we know. It matters for most mass in the universe. So the quantum effects can be crucial. And I personally think it would be striking if they were in fact crucial to the existence of the basic solution we inhabit, which is true in some scenarios. So one class of constructions in this context, developed in the context of type 2b string theory on Calabi-Yau spaces, involves Calabi-Yau orientifolds with flux. So there's a packaging of the flux energy in a superpotential, written down by Gukov, Vafa, and Witten. There are three-form fluxes, and wedged with the homomorphic three-form on the Calabi-Yau, they give a superpotential. It depends on the complex but not Kähler moduli of the space. The low energy effective theory also has a Kähler potential, as any n=1 theory would. We wrote it down in this paper I cite. And alpha prime corrections, so that Kähler potential will always be present. They play a key role in some ideas that build de Sitter vacuum along these lines, and Fernando will talk about that. Now, depending on the geometry beyond this no-scale superpotential of the classical supergravity, there can also be contributions to the superpotential coming from Euclidean branes wrapping certain divisors into space. They were written down in the mid-90s, and they take this basic form I said before. They depend on the exponential volumes of various cycles. And similarly, strong dynamics on branes can give similar contributions with differing prefactors in the exponential. Okay, and that's all well understood. Now, such models most easily yield supersymmetric vacua that you can analyze in various approximations, some of which I'll talk about. But there are also various ways supersymmetry can be spontaneously broken, and that's crucial if we're going to construct de Sitter vacuum. One way of breaking supersymmetry, and there are many, including just using the ingredients I've already described, but I like it for reasons that will become apparent, is supersymmetry breaking by dynamics of branes, because they sort of gauge theorize some of the questions. So a much studied model, I don't have any particular love for it, except that it's a good toy model, is that of putting anti-branes in the supersymmetric warp throat solution of Klebanov and Strassler. We studied this in a paper with Pearson and Berlinda long ago. And the idea is very simple. There's a smooth classical geometry generated by a lot of flux, this warp throat. If you put a small number of anti-branes into it, they carry the sort of opposite supersymmetry orientation to the throat. They break supersymmetry. For small numbers of such branes and small G string times the number, G string times P, there's a stable vacuum visible in the non-compact throat model. Approximations of this vacuum can be made arbitrarily reliable in the non-compact case by choosing sufficiently large flux. Okay, so at small G string times P and at large enough flux, I think it's essentially indisputable that there is a stable non-supersymmetric vacuum. But there are other ideas that tie beautifully to older literature on dynamical supersymmetry breaking as well. For instance, you can use various instanton effects in string theory to break SUSY dynamically by dynamically generating a small scale in models that are more like Faye or Rafferty models of sort of traditional supersymmetry. We did this with Ofer and Mina years ago, and Chris Beam. Others have engineered models of more conventional field theoretic dynamical supersymmetry breaking on branes. A recent paper is by Argurio, Bertolini, Franco, and others. And in a paper in 03, cited there, we suggested some particular scenario for constructing de Sitter vacua in string theory, but it's trivially generalizable to a similar class of ideas that seems suited for the setting and the ingredients I've described. So what were the ingredients? There's a classical flux superpotential. We choose to study vacua where it's small, okay? And that small number from the classical superpotential will provide us with a control. We need to have instantons or strong dynamics to stabilize the volume. The small w makes it consistent to view those as a leading correction in some cases. In others, Fernando will talk about what happens. And finally, to get de Sitter vacua, we need some small supersymmetry breaking from some source or another. It doesn't have to be small, but small is the best if you want a sub-stringy vacuum energy. And that should shift the potential at some minimum to be positive. Okay, so those are the sort of basic ingredients in those scenarios. And the resulting class of models had the merit that there's sort of a clear cartoon of the effective field theory. There's a Planck scale at a high scale, a string scale beneath that. There's a scale of the overall extra dimensions, 1 over R, the KK scale. Beneath that, there's a flux superpotential that stabilizes things at the scale MCS. It removes the complex structure moduli. There's a scale at which the volume is stabilized, lambda. And then beneath that, you get a hierarchy of other scales at which further moduli get stabilized. But it allows one to organize the analysis and try to break the problem down into analyzable subunits. Admittedly, this is a caricature. If you study a model with hundreds of parameters, hundreds of moduli, there could be multiple scales R. You need to make sure all of them fall in some consistent regime for control. And that becomes an interesting issue in modeling.
Just a comment, you are a little bit over 10 minutes. Yeah.
I'm sorry, I'll be done in about 1.5 minutes. Now, I want to make 2 comments before closing. One is the small w that we introduce in this construction classically to offset the energy, to give control over the vacuum, always played a role in traditional model building in the DSP context, because you need to shift the vacuum energy by a small w just to get cancellation of the cosmological constant. So I don't think that's a qualitatively new ingredient in model building. Now, I want to summarize where the status of these models is quickly. I know Pedro said I have a minute at most. So global constructions are obviously work intensive. They're not evidently beyond reach. I'll say more about that in a second. Many partial problems can be isolated and solved. The statistics of classical flux vacua, coming out of beautiful work of Douglas and collaborators, already showed convincingly a decade ago that small w is attainable. The techniques used are generalizations of those that, for instance, let you estimate volume, numbers of lattice points in a volume on the plane by using the volume of the region. Okay, they're fancier versions of that. And explicit examples that verify that such small w is attainable have been found recently by the Cornell group. Global models with instantons in the right configurations to stabilize all moduli were found, again, more than a decade ago. The construction of full de Sitter models in this framework was not a direction of much effort. It's not that lots of people were trying, it's just that it wasn't really clear why to do this, since specific global models will not teach you new lessons but will require careful control of factors of pi. And so there will always be debates about factors of pi. But it's been cleared what to try and do for years, and there's no obvious obstruction. And a group, I'm told, is close to doing this. My own list of good problems is not so much let's make a construction and fight about factors of pi. It's more technology development. The more technology you develop, the more obvious such constructions will become. We can classify local DSP models. We should develop techniques to compute exact superpotentials in string theory. It's possible in field theory. It should be possible in string theory. It should tie to beautiful problems in mathematics. We can further explore the rich mathematics of models beyond Calabi-Yau of the sort Gonzalo talked about. And then finally, there are these deeper formulation issues, which I think, frankly, are a big part of the future. How do you formulate DS quantum gravity? That seems like a good problem to me. Thank you, and I apologize for going over time. Let me unshare.
Thank you, Shamit. So let's switch to Fernando sharing the screen while we thank Shamit for the very nice half of the introduction. Yeah, it looks good, Fernando. Although you are still muted.
Yes, sorry about that. Okay, well, thank you very much for the organizers, for Nathan, Pedro, and everybody else. It's great that you managed to organize this conference in a place that is very close to my heart. And so yes, I wish I can also visit you again and go to some churrascarias and so on. And and it's great to have this opportunity to talk about this subject, in particular with Shami. And I will just give a general discussion, so I will not have time to talk about my own work, but most of what I will be saying is related to the work of me with my collaborators, and this is a list of papers in the last couple of years that everything that I will be saying will be influenced by what we have been working on in the last few years, couple of years. Okay, so yes, so let me start from the beginning, just to be self-contained. So it's two related string challenges. One is moduli stabilization, the other one is to get the sitter. So moduli stabilization, I think, has been there for 100 years since Kaluza and Klein, and I can say that probably it's fair to say that it's only in this century that real progress has been made into finding mechanisms to stabilize moduli. So we should consider this as a success of string theory so far. Of course, it is more challenging once you want to also get the sitter, and of course that's Shami mentioned, is partly motivated by observations, which is very good, and not only for observation of the cosmological constant, but the fact that there is a cosmological constant problem that this fundamental theory, like a string theory, should be addressing. And so I think it is good that in this conference we have been given a lot of space to discuss this subject, which I consider very, very important for string theory itself and also for observations. So we have to start with the Dine-Seiberg problem, which is something already in the 80s. Dine-Seiberg already realized that there is an issue. And the issue is very simple, that a very simple observation. The paper is beautiful. There's a few pages with only a couple of diagrams, but a very nice, clear idea. And the idea is that since we have in general in compactifications, you have the volume over the string coupling, which is the given by the dilaton. So for infinite dilaton is zero coupling, for infinite volume is decompactification. And so the argue is that because we know that 10 dimensions and free string theory is a solution, at some point we have to, whatever potential we get for these fields, it will have to run away for those values, and that is unless there are some quantum corrections that will modify your potential. And so for these quantum corrections to be effective, then it has to be at a strong coupling or a small volume for the two expansion, the alpha prime and the string expansion. So then they said if there are minima of this potential, which will stabilize the moduli, then this minimum natural thing is to be at strong coupling. So either we have a strong coupling or we have runaway. However, we are not interested in either of the two at the moment, because, first of all, we know that nature naturally is giving us weak couplings. We know that the couplings of the standard model, they all are running towards something which is relatively weak. And we also see hierarchies in nature. And so a minimum for one string units, or I mean, the Planck scale, everything will be the same scale, will not be, there will not be hierarchies, and there will be, it will not be fitting with the nature is telling us that couplings, luckily for us, it has to be weak. And for us, it's important because if we can compute in a weak coupling regime, then that's our own limitations, not nature. And so it's nice that the two things match together. So for this, and this runaway behavior matches very well with this Swammland conjectures that Kunru collaborators have been discussing, and Irene and Gonzalo Torraba discussed already in their talks. So this is a major issue, and I think it's important to address the question. So the question is there, and we have to see what to do with it. And so in string compactifications, this is what I can claim is that this is the price we have to pay for string theory for not having free parameters. In string theory, we say what you expect from fundamental theory is that you don't have free parameters. Precisely, string theory has that. But at the end, when you compactify, there are plenty of new parameters that come out upon compactifications. The topological numbers of the compact manifold, the Hodge numbers or so, the ranks of the gauge groups, dimensionality of space-time, and particularly the fluxes. Fluxes of different forms. We have several forms, and there have been many fluxes, and naturally they are quantized, and then you have plenty of new parameters that we can play with those integers in general, those discrete numbers, and to try to see we can there find solutions at weak coupling and relatively large volumes. Okay. The other thing is that there are not only these two expansions, because every single parameter we spend compactification with many moduli, and each of these moduli is an expansion parameter. So at the end, the space, I mean, the potential has to be including all these other expansion parameters, not only the string coupling and the volume. So, but we have to live with the Dine-Seiberg problems. So we will never have full control if this is true, which I think is true. But we may have, we can use these numbers to play and to have weak enough couplings and large enough volumes that we can trust our calculations. And so what I like to say is that this Dine-Seiberg problem is not a disease from string theory, but it's actually a condition. We have to learn how to live with it, essentially. So, and there's nothing wrong, except said that we have to make sure that when we do our calculations, we fit into the regime of that fits the weak coupling. So, and essentially, a lot of the developments in this direction has been done in type 2B. So I will just go quickly because Shamit already said a lot about this. So we have classified the moduli, the dilaton, the Keller moduli, the complex structure moduli, and you have n equals 1 supergravity. So you have the F term component is well known, and we know from the Gukov alpha Witten the three levels of potential is given by fluxes that depend only on the complex structure and the dilaton, whereas it doesn't depend on the T fields and the Keller moduli. And for the Keller moduli, they satisfy this interesting property, which is the no-scale property that you can see because of the scaling symmetries that you have in the 10-dimensional theory. And because of that, this is following the work of Kidins, Kachru, and Polchinski. The F-term potential is positive definite and is minimized when the DWs are 0 for both the S and the U fields, and then that's how they are supposed to be fixed. And T is arbitrary, but this is only a tree-level result that we know that the no-scale property will not hold after we have to consider alpha prime and loop corrections. And then, but the important thing is that these corrections play an important role because at tree level, the potential is 0 after you minimize. So the variation of the potential can be written in terms of the variation of the superpotential and variation of the Keller potential. And there you can see three options. The natural thing is that to have the superpotential, the tree level is much bigger than the correction, which is usually non-perturbative because of the non-perturbative non-realization theorems of superpotential. The corrections to the Keller potential are usually bigger than the corrections to the superpotential because these are perturbative and these are non-perturbative. And so the natural thing to get is the runaway. So that's the generic thing you get a runaway. And what ways out is that to do what KKLT did, is just to tune the fluxes such that the tree level competes with the delta W, with the non-perturbative correction. So that means W0 is much more than 1. And you can do that if you have many fluxes. But then in the large volume scenario that we came out after, you can also play in a different way. You can compare the variation of delta K is competing with the variation of W, in the sense that delta K this is only when you have more than one Keller moduli, which is the generic case. If you have only one Keller modulus, you have to do the KKLT story. But if you have more than one, then the delta K goes like one of the volume, but delta W goes like the exponential of another modulus, e to the minus 8 tau. And so when you compare these two corrections to each other, I mean, you have to compare dynamically. They're chosen to when you minimize the potential, and then you get that the volume is exponentially large, and that's how it's called the large volume scenario.
Normally, you would be more or less on time now, right?
Okay. Okay. So
I mean, on time for your 10 minutes, but overtime for the total 20 minutes. So.
Oh, okay. I'll go fast. Okay, so this is the KKLT and LVS potentials, and this is how you get the minimum to exponential large. And then you have features that the fluxes imply that you have still a Calabi-Yau or warped Calabi-Yau. There is a hierarchy, as Shami said. You have two sets of fluxes for F3 and H3 that will give you a big degeneracy, and so on. So to get the sitter, you may have this antidifferent brain, as Shami said, at the tip of the throat, and that has been probably the main proposal to uplift to the sitter. But then there are other proposals. You have D and F terms in the effective field theory, with something that can be explicitly realized in terms of T brains. The complex structure on dilaton uplift can be DW will be not necessarily zero, but small to compete with the Keller potential, with the Keller modular potential. Non-critical strings or negative curvature, as Shamir mentioned, and Eva has been working on it, and so non-perturbative effects on determinants. So there are several other proposals to get the sitter. And people have, achieved that now a well-defined prescription, including brains, orientifus, and so on, that gets you, first of all, the model stabilization, but also the sitter uplift. So since I'm short of time, I will go quickly to the challenges, which is probably just to motivate the discussion. So this is a story that has 17 years or so. And over the years, there have been a lot of questions that people have been asking about this scenario, which is very well defined. And people have questioned several things. For instance, the fluxes by themselves break supersymmetry. So can we trust then the non-perturbative calculation? You have only a runaway behavior at that time. I claim that you can trust it, and you can verify it after your calculation is done, that the whole thing makes sense. But it has been sort of discussions. The other point is that can you do this treatment in 4 dimensions? Because everything is an effective 4-dimensional theory. So some people believe that doing it in 10 dimensions is better, and I don't see the need to do it to 10 dimensions. But on the other hand, if you do it in 10 dimensions and succeed to get a 4-dimensional result, that is very good. And I think all these people have been making progress on that, and I think that has been making this formalism stronger. The tuning of W0 to be much smaller. You say, how can you get something small from fluxes? But there has been recent progress in several two groups, the Cornell group and the Munich group, to get superpotentials to be much smaller than 1 in a natural way, exponentially. higher corrections to this large volume scenario, that's something we have been working recently, in the sense that what the large volume scenario is based on the leading order correction that people know, alpha prime, which goes like 1 over volume cube in the scalar potential. People have tried in the past to look for other corrections. So the past 15 years, there have been several corrections computed, and they are all subdominant or the same order, so they don't change the picture. But we have been studying now systematically what will be the effect if there will be a dominant correction, which is interesting. Anti-branes have been a source of discussion for the past few years. There is a singularity, the fact that there's no supersymmetry, how you mix it with the unit condensation. And I think there's more or less consensus now that the thing works. I think, except in particular, we can see probably Arthur Hebecker will have something to add. If you have that people call bulk singularities, that is still a challenge. And then the Talpor problem that Mariana Graña summarized in her talk this morning. So I think that those are challenges and subjects of discussion. So an alternative to, so people say, well, what about, is the sitter the only solution? No, it's not the only solution. You can even...
Fernando, I think maybe it would be good
Yes.
to open up for the discussion.
Yes, well, one minute and I finish, yes. Quintessence will be a possibility, but you need to get quintessence, you need exactly the same techniques that you needed for the sitter, and on top of that, you need the runaway. So in that sense, it is interesting to get it, but it's equally challenging, if not more. So, okay, to finish, that was open questions, better control on alpha prime and quantum corrections. Realistic phenomenology, I concentrated only on getting the sitter, but it doesn't matter to get the sitter if you don't have the standard model somewhere. So for that, I invite you, my student, Andreas Schachner, will have a poster session, so we have a recent work on this. Moduli stabilization in F-theory in general, that would be important to take care of issues like open string moduli that have not been properly studied. And then populating the landscape. This is, as I say, it's not only a way of getting the sitter, but it's also, in principle, is the only way to address the, I like to say, is probably the worst solution of the cosmological constant problem, with the exception to all the other ones. So in the sense that this formalism provides a potential for solving the landscape to solve the cosmological constant problem, but we need to understand better the structure of the landscape, transitions between different vacuum and so on. And I have been working on this recently, and I found that there's plenty to be understood on the original work of Coleman, DeLucia, and others, that I think probably new techniques that people have been using in a positive way recently for black holes, using semi-classical gravity, probably they can be used to understand better this vacuum transitions, which is a way to populate the landscape. Okay, I stop here. Sorry for taking time.
Okay, let's thank Fernando and Shamit. And let's open it to discussion. So please, if you are discussing, if you plan to discuss, keep your camera on, raise your hand and wave if what you want to say, to ask or comment is related to what is being discussed right now. So that, and that's it. And I will be calling people, but if Fernando or Shamit find that there's someone that makes a lot of sense to call at a given moment, just override me and call. So Thomas.
Yeah, thank you. So what was interesting, and I think it's good, is that we heard very optimistic view on the sitter space in string theory. And I think that's probably a good thing, because the recent years we have been hearing a lot of very, the opposite sound, okay? But nonetheless, I just want to confront Fernando and Shamit with the fact that recent polls in our field have shown that the situation, that we are really polarized, okay? There's actually now a way bigger part of our, our community that is believing we haven't succeeded in a single de Sitter solution so far. And then some of them are even thinking it might never be possible. So I'm just saying, this is a situation. What is going wrong? I mean, right? We are doing mathematics. We should, in the end, agree with each other, right? That there should not be any room for belief, but we're in a very awkward situation. And I would just like to have your take on this.
Okay.
I'd want to make a comment quickly.
Okay. Do you start or should I start?
Go ahead, Fernando.
Okay, thank you. No, just I think that's good that you raised it, Thomas. Yes, my take is you know, you tell me, they say, I will not believe any calculation unless you are in the full control. That's what I emphasize, the Dine-Seiberg problem. So then we all agree it's runaway. That's not, but that's something we already knew many years ago. So runaway is a natural thing, or this is strong coupling thing. So, but then we have this ingredients of this many integers so that you can play to get to weak coupling. So, so in that sense, if part of the community don't believe unless you have full control of the expansion, so it's good for them. That's the way to think, and that's. But I will not lose any sleep about that. So and so it's I don't think that it's a big problem to trust the expansions, as long as you and this is, as I say, it's a price that we have to pay for string theory not having free parameters. And so that means that you have to work, assume that you have weak coupling, and then check if the result you get large volume and weak coupling that you can trust, and then how large the volume and how weak the coupling probably is a question of taste. But I think that's a very logical and consistent way of dealing with it. And I don't see any reason to.
But then, Fernando, sorry for interrupting, but then what is weak enough coupling? What is large enough volume? Is it like in field theory? You think of an asymptotic series and you're happy whenever the number is smaller than 1? Or is it really distinct from field theory, is what some people would be saying? Like the question of Ed Witten about the talk of Gonzalo was about this. You know, wouldn't we want parametric control? Because maybe this is not like ordinary QFT.
I agree with you, and there is no solution to that. I said, if you want to go to as large a volume as you want, you will go to the runaway. And now, yes, but at the end, what we are here is to describe nature. We know that the runaway doesn't work in this way because this runaway of the volume or the dilaton is not good enough for quintessence. And I think some people mix quintessence with runaway, which is not correct. I mean, runaway is very generic. Quintessence is not generic. So getting quintessence is as challenging as getting the sitter. And and as I say, it's a condition for string theory. But it's not that we have to work as hard to evade the Dine-Seiberg problem. That this is different, and we have to live with it. And so that's what I say. If it's a volume 10 to the 3, 10 to the 4, I will be happy. Maybe you will prefer 10 to the 6. So that is that's the question of taste. And probably Shamim will have something to add, I guess.
Yeah, let me add a little bit. First, thanks for your question, Thomas. I think it's a great question. I'm going to separate it into 2 parts. Part of it was a sociology question about what people believe. To be a little blunt, I don't really care what people believe. The history of science is that correct ideas will triumph. And so as a function of time, people will do this with their beliefs. Just look at US elections. The other part was about science. And this part I agree with 100%. The best parts of string theory so far have been the parts that can be essentially reduced to math questions. And so far, since the majority of work on de Sitter spaces and constructions that can't be asymptotically weakly coupled or an asymptotically large volume, there's no n like the n of Freund-Rubin, there is always going to be room for doubt, as Fernando said. And there you can debate. And you know, the most logical answer is you should be at the point where you can compute the next correction and convince yourself it's small enough to preserve the sign of the vacuum energy and leave the minimum. But let me point out what I found a little bit frustrating. In KKLT, part of the point of the construction was to isolate certain problems that are math problems at this stage that don't require that kind of belief. The question of whether a classical flux vacuum can have small W naught. This is a math question. It can be answered decisively. It's a question about classical physics. It's algebraic geometry of some relatively pedestrian sort. Douglas and Denef answered it under extremely plausible assumptions, much more rigorous than most of physics. More than a decade ago. Explicit constructions have answered it more recently. They will get more explicit with even smaller values soon. That's a math question. I think it's been answered. I don't think we need to debate it anymore. The question of an asymptotic supersymmetry breaking state in a non-compact throat is a question that can be answered. You may not agree on the answer, but with a small number of probe brains in a non-compact geometry with an arbitrary parameter n, the question can be answered. That becomes a mathematical physics question. So I believe a lot of the mathematical physics questions do have bearing on pieces of these constructions. I'm sure the same is true of LVS and other constructions that Eva and Gonzalo have talked about. And those can be answered. And to my mind, in many cases, they have been answered and shouldn't appear on lists of these discussions because that isolated bit of the problem you can answer. That does leave the global question. And then I agree with you, there's going to be, unless you have a construction with an asymptotic n, a question of whether your control is good enough. And the best you do in physics is you try to estimate the size of the next corrections. I hope that was useful, and thank you for your question.
Since I'm sure this is going to be a fun discussion, let me go over the people that did not participate yet in these discussions, and then I'll go back to the chronological order. So maybe Fernando.
The other Fernando, I guess.
Yeah,
Fernando, me or Fernando?
Yeah. Okay. Yes, please.
Thanks. So yeah, well, I just wanted to make a comment because you put in some of the challenges of all these stabilization scenarios that are around. And it's also one of these math problems that Shamit was talking about, this moduli stabilization of complex structure, dilaton, or complex structure in F theory. As a matter of fact, we kind of analyzed this from an analytic way 1 month ago in a paper in the large complex structure limit. And there you can see a bunch of things. I mean, you can actually see how many moduli are stabilized for an arbitrary number of initial moduli. It depends on the rank of a matrix. And actually, when the rank is not maximal, you end up with a scenario, or well, it's one of the cases is a scenario pointed out by Dermitas, McAllister, and so on, where you get a small W naught. So it gives you a lot of power. And one of the things that it shows is that this tadpole conjecture that was presented today by Mariana is simply not true. I mean, it's a very...
Actually, this is not correct. Your vacuum actually doesn't have... Your vacuum has problems. You don't have the metric. You're just assuming some metric from the throat.
I mean, please
let's just Fernando finish. And then
sorry, it's not correct. It's a scenario. It's not a construction.
It's a
the scenario and construction. Let's put US dollars and Zimbabwe dollars and two different things. Scenarios are nice. You don't have a construction.
If I cannot talk about... Okay.
No, but
since you are so, I mean, okay, it's really a math problem. So you can go through the math and tell me what's wrong.
There's a metric.
And actually, as a matter of fact, this kind of vacua, they are not even, the first one, they are not even from my paper. They're from a paper of Paltio and collaborators of 2008. So there, for general Calabi-Yau in type 2b, you can generalize it to F theory. It's a math problem, and then you can go and solve it, which is what we did. And actually, the fact that Mariana decided not to talk about it, I really don't understand, guys. I think we should have a more...
We thought about it for a long time.
Especially in this conference.
We discussed it a lot. It's a scenario.
Example
and we
for
believe
everyone.
There's a problem with the metric.
Please,
you cannot
I'm not interrupting you. I'm just trying to finish one sentence. If you would be some kind of let me do it. Yes. Thank you. No, I'm done, actually. Whatever. I mean, read the paper and let me know if you agree.
We read it.
I mean, I'm
not
saying
time ago we discussed it for hours.
I'm sure that for many compactification it could be an issue, but the type of conjecture is wrong. And you can go and construct your favorite Calabi-Yau fourfold and apply the techniques that we did and see that, well, this bound doesn't need to exist. We tried to qualify it, but okay, we didn't. We tried to see if how could it work, but we just found counterexamples to it, and we did only scratch a tip of the surface. So. Yeah, that was my comment. The math problems are nice to look at because then there's no controversy. And this is one of them. Thank you.
Yeah, thank you. It's interesting.
So do we maybe I would suggest Arthur?
Sorry, will you allow a comment, Pedro?
Yes,
or if
please.
not,
if your comment is related, please. Yeah, just wave. Sorry if I did not see you.
To what Arthur said, but just to the general point that Shamit and Fernando made, if you'll give me a minute only. You know, I think it's true that these constructions don't have parametric control in the sense that Shamit was mentioning, Fernando said, and I think it's completely correct that we should. Well, at least the constructions I know don't have any parametric control. And I think, therefore, it's completely correct, given that this is such an important question that we should be very cautious, right? And I think that's a good attitude. I personally have that attitude. But I think one way to try and make progress is to try and compute corrections. Because if you don't have parametric control and you say, I have a small number and it's small enough, then the practical way to do it would be, okay, let's try to compute the first corrections and see, are the corrections small? This is a physicist's way to do it. And I bring this up because I think there's progress, and we heard some of it in Ashok Sen's talk on trying to compute with Raymond, backgrounds and so on. And I think that technology is the kind of thing which might allow us to get more control as we go forward. Okay, that's my small point. Please go ahead.
Let Fernando maybe respond, and then we'll go to Arthur.
Yes, I think it's a good point, Sandeep. So something that we have been working on is that the corrections that we use in the large volume scenario is the leading order in alpha prime that people have computed. They are the leading order in 10 dimensions, but they are the leading order in n equals to 2. But in n equals to 1, people say, well, there may be other corrections that we may have missed. That could be because they are alpha prime cubed, so it may be alpha prime to the 1 or alpha prime square in that sense. And so we have been trying to deal with them. So recently we managed to prove that what is the alpha prime to the 1, which would be the problem was alpha prime square, give us something like we call a standard noise scale, that they contribute to the kinetic terms, but not to the potential, for an interesting property. But alpha prime to the 1, they may be dangerous. As something that I think we want to make sure that if they are there, what kind of effect they have, or if they're not there. The only thing that we managed to prove so far is that they are not there at tree level. So any correction will come with loops. So it will be loop suppressed compared to the other one. So then again, you have a competition between the two, one alpha prime to the cube to alpha prime 1 with the loops. So you can still cancel each other without breaking perturbation theory. So that's the best we have achieved so far. But I think there's plenty to be done in that direction. And I think I welcome your comment. Yeah.
Thank you.
I think Gary, since he's waving, he would have priority, and then we'll continue.
Yeah, so it's just a quick follow-up to this discussion. So in one of Fernando's slides, you mentioned that you don't see the reason why one would like to go beyond four-dimensional EFT in these string constructions. It's precisely related to the discussions we are having now. Since we agree that there's no parametric control, it's extremely important to work directly with the microscopic construction and not just stay within the four-dimensional effective field theory.
Well, let me tell you my argument just addressed to me.
I was promised to be able to ask a question.
Sorry?
I have been forgotten. I would like to still ask a question at some point.
Okay, you and
okay. So probably Arthur has the same thing. No, I fully agree that but for me, I mean, this is an issue about describing Gaussian condensation, which is a four-dimensional strong coupling effect somehow. If you want to do it in a formal way in 10 dimensions, you need much more than that. So whereas in 4 dimensions, it's very well settled. I mean, the question is very well posed, and you can answer the question how you can get the effective superpotential and so on. In 4 dimensions from Gaussian condensation. People have been working on that for many decades already, and then you know what to do. From 10 dimensions, of course, you need to know to get to understand string theory at that level. You know, the Gaussian condensation is the lambda, which is is something that requires some strong coupling knowledge of the theory. So I welcome people trying to do it. But again, I think that I'm a 4D person, so with the 4D effective field theory, if things work, I will be surprised if things will not work with the 10D. And but I mean, I have nothing against people working on the 10D picture. If you achieve that and you get it, as I said also in my talk,
my comment is not specific to
it gives strength to formalism. So all these challenges that I mentioned, I think they're good challenges. All these are, by being questioned and by being answered, they're making these scenarios much more robust. So I would claim that both LVS and KKLT are far more robust now than they were 15 years ago. And because all these things have been questioned one by one, and people have been finding answers. So I think the more scrutiny we do, the better. And but it's essentially that I hope you probably I didn't say I said it probably too strong in that sense. I will apologize, but I welcome this the effort intended.
Well, let me suggest now. Let's go Arthur, then reply from Fernando or Shamit, then Ashok.
Thank you very much. So I do not want to argue with Gary Xu and Fernando Quevedo. I totally agree. The standing picture, in my opinion, is also important, but I have a much more simple-minded and direct question to Shamit, because I very much appreciate his comments about W0 being established, that can be small, that the throat is probably very much established. And I've always been a big supporter of KKLT being a simple toy model in parametric control, where we really are convinced that things work. And recently there has some criticism of this has come up by Carter Moritz Westphal, then we worked on this, and Carter Moritz again, which basically says that the throat has become so large, if you want it to be deep enough, that basically you are forced to have the Calabi-Yau, the bulk Calabi-Yau, in a strongly warped regime, and then you get either singularities or strongly curved regions, which means exactly that you lose parametric control even at the most superficial level, or the one curvature is really bad. And I wonder whether you knew about this point, or whether you follow this recent debate, and whether you have an opinion about this, how to overcome this. For me, it seems to be important, because I would like to sell to a skeptic a clear, simple model, independently of pi factors, as you correctly stated.
Thanks, Arthur, for the question. I want to answer. I'll say what I can about your question, which sadly is very little, and then I want to make some comments about what's in the chat. So first of all, I have to admit I'm otherwise occupied, so I haven't been able to attend all the discussions relevant to this at Strings, or to keep up with the papers from the last month or two. On the issue you're raising, which is when you glue a throat with reasonably large flux, quantum number, I guess n, we could call it, into a Calabi-Yau, does that constrain how large what I'd call the Planck brain in Randall syndrome, or the head of the Calabi-Yau, the bulk, has to be, which would have interplay with the instanton effects? I understand the question. I think in a toy model, the most recent work that I know about is this paper of Moritz, which shows that in a model where, frankly, the fluxes aren't that large, a K3 toy model, 7 brains arrange themselves to avoid any particular issue. And, the GKP construction, assuming a large enough Euler character, allows you to make a throat with flux up to the Euler character of the bulk in the no-scale regime with a dialable volume. And I don't see a part of that construction classically that breaks down. Now, your question is about what happens quantum mechanically, and can you stabilize consistently with the bulk being not so big when the throat is large? And I have to just admit, I haven't looked into it yet. So KKLT is now an 18-year-old paper. There have been questions, over many years that I've tried to respond to with decreasing, enthusiasm. So that's my psychology. So I plan to look. I hope it will be clarified, but I haven't looked. Let me comment a little bit on other questions in the chat, if it's okay. Is that okay, Pedro? Okay. So there's a question about.
I think this one is worth your effort. Actually, my personal feeling, of course.
Yeah,
that one is worth your effort.
Okay, I'm not arguing against that. I'm not trying to dismiss anything. I'm busy.
No. It's just a private really comment that I'm really curious about your personal opinion on this particular issue.
Okay, thank you. I want to comment on some other things in the chat. There's a question about parametric families of de Sitter vacua with really an n that can go to infinity. I don't know of any obstruction. I think others have said that in the chat. I think that would be great. I think they would be unrealistic. Who cares? I think there's no reason they shouldn't exist, and maybe we'll find some. There's a question about what does it mean to have small w naught if after including alpha prime or g corrections, that's not a solution of the classical string theory because there's a tadpole. That statement is correct. If you start with a solution of the classical flux equations that break supersymmetry, a small w naught, and do loop corrections, you'll find, oh my God, the first loop correction leads to a runaway because the tree level solution was a no-scale supergravity. This has been a standard issue in string theory since the 80s. No-scale supergravities arose actually much earlier, in fact, before string theory became popular. And we answered this in 2 papers. GKP gives a precise meaning of what it means for W naught to be non-zero. There is a classical math question. W naught being non-zero but small is an answer to that question. And if W naught is small enough, that resulting effect is treatable in effective field theory as long as there are other scales in the potential that are below the Kaluza-Klein scale. You could treat that problem. And we wrote a whole paper responding to this criticism in 2018 with Trivedi. In fact, I'll give you the archive number. It's 1808.08971. So for that question, you can get my answer at least there. Those are the questions that I saw in the chat. That at least is my attitude.
More chat questions.
Say again?
Let's come back to more chat questions a bit later. Let's now move to Ashok, and then we revisit some of the chat.
Okay, yeah. So I just wanted to add a philosophical note that it's good to have parametric control, but I think string theory has many surprises. And so my feeling is that even if you get a factorial coupling constant like 1/2, you should not worry. Just do the calculation and see if you get something sensible, right? And I thought I'll remind you that in the study of tachyon condensation, the parameter that we had was 4/3√3. And if orders of magnitude, a few orders in the expansion, people got like 1 in 10 to the 10 accuracy, right? So you shouldn't be too keen on parametric control. It's good to have parametric control, but string theory doesn't always work the way a normal quantum field theory works.
Very good, very good.
Thank you, Ashok. Let's go on with still the people that have not participated in previous discussions, and then I will go back to the beginning. So Senarath.
Hi, thanks for calling on me. So I have a somewhat different attitude towards the construction of de Sitter vacua. I mean, it seems the reason why people are trying to construct a de Sitter vacua is because the cosmological constant has been observed to be positive. But this is a measurement done at cosmological scales. String theory calculations are done at the string scale or the Kaluza-Klein scale. When you run down from the Kaluza-Klein scale to cosmological scale, a lot of things can happen. For instance, an ADS vacuum, and we can produce examples of this, can become at very large distances a DS vacuum. So even if somebody proves that that string theory cannot possibly admit DS vacua, that does not rule out string theory. It just tells you that at that scale, you cannot produce a DS vacua, but it may also be viewed as a prediction that the low energy physics is such that at very large scales, you end up with a DS vacua. Well, that's all I had to say.
Thank you. Fernando or Shamit, you want to respond, or otherwise I'll finally give the word to Ignatius.
No, I agree with Shanta. We are collaborating, so we have discussed this in the past. So I think, yes, he has a good point.
So Ignatius, sorry for keeping you waiting for so long. Please.
I have a comment on the Dine-Seiberg problem. I think it's analogy. It's fair to say that it is an analogy with a similar problem in field theory. If you have a field theory and you, with one coupling constant, and you try to compute the scalar potential, which has a discrete, let's say, symmetry, and you want to show that it has spontaneous symmetry breaking. This is never, you can never do it in perturbation theory because precisely the same problem happens, because for weak coupling, you have to put the two orders of perturbation theory at the same level. A way out of this in the field theory is the Coleman-Weinberg mechanism, in which the theory has two couplings and the logarithmic corrections to scalar potential. And then we know how it works. So I'd like to bring this in the discussion. We tried to implement it recently to a way of stabilizing moduli based on perturbative corrections, but using precisely logarithmic corrections in the scalar potential. And we had a working example in which W0 doesn't need to be small.
Okay. Well, thank you, Ignacio. It's very interesting. I saw your paper, but didn't see the analogy with the Higgs mechanism. I'll take a look. Thank you.
Ivano?
Thank you. Hi. There are recent swampland considerations, and there are 2 recent papers about this, that talk about gravitino masses versus the effective field theory cutoff, right? And there seems to be a tension, at least in some settings, between low energy SUSY breaking and separations of scales in the effective field theory. So I was wondering if you had any comments about this regarding, the models with low energy SUSY breaking when constructing the Sitter vacuum.
I haven't followed those papers. I have no comments, but maybe, I don't know, Shami or someone else in the...
I can say something.
Yeah, please. Yeah, and remember, please wave when you want to reply to some comment. And
yeah, that's a comment. We have done an old work in 1988, trying to break supersymmetry with Gaussian models. And we have shown at that point, that once you try parametrically to get a gravitino mass which is very light, then you get a tower of states. In that case, reminds compactification. So it was very old result. Apparently, I don't know if people knew it recently when they.
So there is some sort of tension there between having
but this was
consistent.
The assumptions there were well defined. I mean, were Gaussian models, but it was completely, it was controlled. It was a result within string theory.
Thank you.
Okay, can I make a comment also about that?
Go on, Shamit.
I'd like to say that, in the spirit of an earlier response in the cosmology discussion, there's a piece of string theory and supergravity which is taking the known effects and potentials, computing the results, and seeing what happens. In that framework, with known superpotentials and Kähler potentials, and accepting that one can use approximations that are self-consistent, there's no problem getting gravitino masses beneath the KK scale. Now, in asking your question, you said swampland considerations. I don't know what swampland considerations precisely means. Some of them are rigorous, like bounds on signs of higher derivative terms. I don't think there's any inconsistency with bounds on sizes or coefficients of higher derivative terms. If you mean something more general than that, then my personal attitude would be, these are speculations and I trust the calculation. If you mean precise bounds, like these things about higher derivative terms, then that's an interesting question.
Yeah, to my knowledge, what I mean is, reading the papers is like extrapolation based on concrete scenarios that are not necessarily realistic in any way. So it's a conjecture based on some existing models which are not necessarily related to these constructions. So yeah, I get your point. Yeah. Thank you.
Eva?
Okay, so there's a lot that's been said that's already covered things I would say, but the opportunities for parametric control would be things like large D and say topological parameters in negatively curved spaces. But it's not, in my view, it's not needed as long as you have weak but finite couplings. That's also okay in the spirit of Sen's question as well. I was hoping to maybe move the discussion towards some of the interesting questions that that were brought up on the more conceptual side. So if we use KKLT, for example, and we ask what could be the holographic dual, there's an idea that I pursued a while ago, and I wanted to just bring it up in this crowd to see if anybody can get traction with it. So there's a particular set of fluxes that one has in KKLT, the three form Ramond and S fluxes. And if you trade the fluxes for branes, if you did that in the ADS5 times S5 theory, you would get the ND3 branes, and you would kind of infer that you have this N equals 4 super Yang-Mills theory living on those branes, on their Coulomb branch. If you look at KKLT and you trade fluxes for branes, you get an interesting network of NS5 branes on which you have various strings and string junctions that end. And if you look at the sort of the spectrum of those, and their dynamics, it fits well with things like counts of vacua and with how the complex structure moduli stabilization maps to fixed couplings in the resulting 3D gauge theory. So I just wanted to throw that out there because I find it an interesting approach to how to think about the dual of these examples. So again, in a nutshell, it's trading what fluxes are there for branes and seeing what lives on those branes and trying to infer the dual content from that.
Maybe I can just I think it's a very good point. Eva, I remember you gave a talk, I think 2003, I guess, in strings. And yes, we went through your talk. And we have a paper actually called KKLT, CFT, and LVS CFT dualities, trying to make sense of both. In the case of LVS, we found that the corresponding CFT should be extremely well defined with only one operator with a scaling dimension very well defined, and so on. But I think not that much was explored after that, and I think it's a good avenue to try to understand better if there's anything to be learned with the CFT. Yeah, thank you.
I've understood that Ofer Aharoni has a comment to make. Could we allow Ofer to speak?
Yeah, of course.
Well, my comment is a sort of trivial one, but I don't think it's been mentioned, and that is just that all these constructions that give you de Sitter space, if I understand correctly, they can also very easily give you anti-de Sitter spaces that are non-supersymmetric. So in principle, a way to make this whole story on better mathematical footing would be to find the CFT duals to these non-supersymmetric anti-de Sitter vacua that should have large gaps and so on. So if we could prove or disprove their existence, that would of course be a good way to test this. I mean, but again, I don't think that's necessarily a practical way, but at least in principle, that would be one way to make this a well-defined question.
I completely agree. And actually a well-defined math question there is just finding the situations in which a separate KK spectrum with a scale parametrically different from the ADS scale appears in the spectrum in a CFT and putting constraints on those parametric separations of KK towers. And I think that's a little bit beyond what the bootstrap people can imagine doing today, but I'm not a complete expert. I asked DSD about this a couple of years ago.
Sorry, could I just add to Ofer's point though, what Dan said in the chat, which I agree with, those ADS vacua have no reason to be stable. And given that they're not stable, they actually need not correspond to a CFT because those bubbles hit you within an ADS time. Am I missing something, Ofer? Would you agree with that?
Well, I mean, from the point of view of the potentials that you guys draw, I mean, they do look like they're stable, right? I mean, they may have some instabilities, but it's not obvious that they would have instabilities.
Well, the flux decays, for example, would sort of take them. A given one would.
Well, that may depend on the situation. I mean, it's not obvious that all of them would be.
Okay, fair enough.
At least I don't think it's obvious that all of them would be, but yeah, that's certainly a good point.
Okay, thanks. Fair enough.
Let me do something because people might have schedules that they might have to leave, and I don't want people not to thank Shamit and Fernando. So let's thank Shamit and Fernando, but continue. So let's close the official informal discussion. But of course, there are so many people with the camera on, so many people with the hand raised. So I think if Fernando and Shamit can stay a bit longer, we can continue a bit more.
I need to run in 10 minutes, but I'm happy to stick around for 10 minutes.